So there are two problems here. You're going to see that both are coupled. See, this I think each of you will understand. Hello, listen to me here. The pulse compression problem is the following. You have some finite pulse t, right, of some duration. Any pulse, very long pulse generally. So the idea of pulse compression is you want to find a filter which will compress it into the, at the output. All the energy is compressed. All right, so that's the problem. So it's up to you now. So for a given waveform, can you design a filter which will do the job? So remember, one person may come and say, I can design this. That's also a compressed pulse compared to this. All right, so how are you going to do it? And if you compress it, it's like the bound. You can always make a better compression. So I would say this is better. This is even better, right? So how do you design this filter for a given pulse? This is very important, especially in applications. And even a more challenging one. So at the least, even if you have no idea, maybe you can do certain simulations. Take a pulse, take some filters, look at the output, plot it. And but we'll discuss some of it today to give you an idea. But consider this is called a constant modulus or constant envelope signal, right? Because if I call the signal to be S of t, this signal has the property that absolute value of S of t is 1 all the time. That's what I mean by constant envelope, right? What is an example of a constant envelope signal? Anybody? What? Sine is not constant envelope because you see the value here is 1. The value at some other time is not 1. See, this property is not satisfied for sine, right? Sine is bounded by 1. For sine, this is true, right? But you are very close. S of t equal to e raised to complex sinusoid is, of course, constant envelope. Sine also we usually say constant envelope, or at least it is bounded, right? Sinusoid or anybody know? Anybody has seen this signal or knows about this? What is this signal? No? Anybody else? So we are talking about pulse compression. If you don't, I guess you have a topic. If you don't have a topic, but in any case, the problem is the following. If you have a pulse, how do you design a filter so that the output is compressed? And more importantly, you may want the input signal to be something like a sinusoid or complex sinusoid, which has a constant envelope, and then the output you want to look like this. So in fact, the homework is using MATLAB. I give you both the, at least I'll give you some idea about how to construct this. It is related to the previous problem. Then you just plot it and see which one is good. Now where is this? See, in a radar, for example, you transmit a constant sinusoid or something. Okay, actually in radar it's more complicated. You wait and then you transmit another pulse. But suppose it goes and comes back, right? And suppose there are two targets here, okay, target 1, target 2. So this waveform goes and comes back. So the return signal will look like this. Of course, now you need to, so this is the signal that has come back. It's actually more complicated because there will be noise, right? So it may be messier. I don't want to. So now you want to, whatever you receive, you want to pass it through a filter. Some processing need to be done so that the output will look like this, so that you know that there are two targets. Because looking like this, if the output is very wide, then the two outputs may look like this, right? So you will miss that. If the compression is not good, so if the compression is like this, then if two targets are nearby, the output is going to look like this. If the compression is good, then even closely spaced targets you can recognize. That's the idea of pulse compression. It's a very important. But you may say, why don't you transmit a very narrow band, I mean, very short pulse in the, that's impractical, because if you want to transmit a pulse of only duration 10 raised to minus 6, its amplitude will have to be very high. And so what generally is feasible is you want to transmit very low amplitude pulse for a long time. Okay. But then if you can pass it through a filter and make it look like this, that's what we mean by pulse compression. Question is, what is this black box, H? See, this very low amplitude, so this is almost like a May 8, right? And I think we are back 13th, and 15th is final exam. So I only have 2 classes, and this second class, the second half we will have presentation. Okay. So if you, Sebastian, if you want to make a note, next week we will meet here, of course. You may want to make a special note for that, because as you know, university has declared that Tuesday as the Thursday class. So we'll meet here again. And that will do the, right.
So that Tuesday you'll have class.
Yeah, right. And the second half is presentation, but we can videotape that too, that way they can see, right.
Okay, no problem.
So remember, you will be on TV on 15th, right. So what I'm trying to say is that you need to get your presentation ready, right. So that's in less than 2 weeks, right? In fact, exam is in 2 weeks. So there are 2 problems here. You're going to see that both are coupled. See, this I think each of you will understand. Hello, listen to me here. The pulse compression problem is the following. You have some finite pulse t, right, of some duration. Any pulse, very long pulse generally. So the idea of pulse compression is you want to find a filter which will compress it into the, at the output. All the energy is compressed. All right, so that's the problem. So it's up to you now. So for a given waveform, can you design a filter which will do the job? So remember, one person may come and say, I can design this. That's also a compressed pulse compared to this. All right, so how are you going to do it? And if you compress it, it's like the bound. You can always make a better compression. So I would say this is better. This is even better, right? So how do you design this filter for a given pulse? This is very important, especially in applications. And even a more challenging one. So at the least, even if you have no idea, maybe you can do certain simulations. Take a pulse, take some filters, look at the output, plot it. And but we'll discuss some of it today to give you an idea. But consider this is called a constant modulus or constant envelope signal, right? Because if I call the signal to be S of t, this signal has the property that absolute value of S of t is 1 all the time. That's what I mean by constant envelope, right? What is an example of a constant envelope signal? Anybody? What? Sine is not constant envelope because you see the value here is 1, the value at some other time is not 1. See, this property is not satisfied for sine, right? Sine is bounded by 1. For sine, this is true, right? But you are very close. S of t equal to e raised to complex sinusoid is of course, constant envelope. Sine also we usually say constant envelope, or at least it is bounded, right? Sinusoid or anybody know? Anybody has seen this signal or knows about this? What is this signal? No? Anybody else? So we are talking about pulse compression. If you don't, I guess you have a topic. If you don't have a topic, but in any case, the problem is the following. If you have a pulse, how do you design a filter so that the output is compressed? And more importantly, you may want the input signal to be something like a sinusoid or complex sinusoid, which has a constant envelope, and then the output you want to look like this. So in fact, the homework is using MATLAB. I give you both the, at least I'll give you some idea about how to construct this. It is related to the previous problem. Then you just plot it and see which one is good. Now where is this? See, in a radar, for example, you transmit a constant sinusoid or something. Okay, actually in radar it's more complicated. You wait and then you transmit another pulse. But suppose it goes and comes back, right? And suppose there are two targets here, okay, target 1, target 2. So this waveform goes and comes back. So the return signal will look like this. Of course, now you need to, so this is the signal that has come back. It's actually more complicated because there will be noise, right? So it may be messier. I don't want to. So now you want to, whatever you receive, you want to pass it through a filter. Some processing need to be done so that the output will look like this, so that you know that there are two targets. Because looking like this, if the output is very wide, then the two outputs may look like this, right? So you will miss that. If the compression is not good, so if the compression is like this, then if two targets are nearby, the output is going to look like this. If the compression is good, then even closely spaced targets you can recognize. That's the idea of pulse compression. It's a very important. But you may say, why don't you transmit a very narrow band? I mean, very short pulse in the. That's impractical because if you want to transmit a pulse of only duration 10 raised to -6, its amplitude will have to be very high. And so what generally is feasible is you want to transmit a very low amplitude pulse for a long time. Okay. But then if you can pass it through a filter and make it look like this, that's what we mean by pulse compression. Question is, what is this black box, H? See this very low amplitude, so this is almost like a spread spectrum signal. So somebody else may not be even know that there is a signal around like this. So low power, but then you want to design so that all this energy is compressed and it comes like this. Because then the advantage is, as I had began to plot here, the noise, of course, may be input, it may be large, but if the signal gets compressed, signal is going to stand, and the noise also gets somewhat compressed, but the signal will stand out at the output above the noise, and you can. And if this compression is good, and if there is a second, remember this, you transmit, it comes back, but if there are two targets, there will be two such pairs coming. So there may be one more here so that you can see two blips. So the homework I am just asking, I actually will tell you one possible filter, but this is again, you can do if anybody is interested, a thesis can be done. I don't think this is still completely solved the problem. So this is the problem. You have it's also good in communication, right? Bits are coming in, so if you transmit a bit during this duration, right, because of the channel, the bit will, so of course the bits are coming in, sequentially, right? A 1, 0, 2 1s, 0, 1, etc., right? And you're modulating it somehow. But then there is channel, right? Of course, if you assume that it's an impulsive channel, a perfect channel, the same thing will come out. But if you assume that the channel has some response h of t, the 1 will look like this. Then the 0 is going to look like this. Then the 1 will look like this, things will get spread out, right? Of course, this is inter-symbol interference. So again, you need a receiver which will begin to compress so that this information will be compressed within this. But if you can do better compression, that's even better, right? So it's useful then you can use some sort of threshold, what you do, optimum threshold detector. Remember, we went through all this. So the compression is crucial. So that is an art. You can spend some time and to see how to design filters which will do this. So the problem is simple. I have a pulse of some duration out t. I want to compress it. It's easy to measure, right? Because if two of you say that you have done compression, one looks like this, the other one looks like this, then remember, of course, here you could say the black one has lower side lobes, whereas the red one's the side lobe. So you will have to see. Suppose this side lobe is already 30 dB down, then these glitches may not matter. Generally, what matters is the main lobe. So the main lobe. So if you have an idea, if you make a definition how to define the main lobe of this and the black one, then you know that the main lobe, as you can see here, the red one is, of course, a better compressed pulse. The question is, how do you design that filter? So there's some work can be still done, and I'm going to give you some motivation going through this one. But if you feel you can do it, then really the problem that people are interested both in communication and radar is input signal is constant envelope, and then what is the pulse compression. The reason I'm saying is we are going to study something called a matched filter, and one of its side results is that it also compresses the input pulse. So the problem is just continuing with last week's, remember we went through power spectrum, so I'm going to show you an application. Remember, we studied this much. You have a signal, or you have a system with the transform h of omega and signal x of t or x of n, discrete, continuous or discrete time. And same thing here. You have continuous or discrete time. You get y of t or y of n. What we have learned is the output power spectrum. If this is Whiteson stationary, we learned a couple of weeks back, this is Whiteson stationary, implies Whiteson stationary, right? And then you have the autocorrelation. Its Fourier transform is the power spectrum. What we showed is that Fourier transform of any autocorrelation function is non-negative, and that's the Fourier transform. Similarly, the Fourier transform here of the output autocorrelation is the output power spectrum, and these two are related as what? What is the relation?
Absolutely.
Right. So multiplied by h omega squared, okay, or h e raised to j omega squared, depending on whether the system is discrete or continuous. So I'm going to show you an application of this in that suppose the input signal is coming in with noise. So you transmit, let's say you transmit a signal like this, or whatever, a pulse or some shape. So it goes there happens to be a target, so it gets returned. So what is coming back is this one. See, this same signal came back. So you say, no problem, I can see it, I don't need any filter because you saw the signal coming in, okay? But in real world, it is not like this. So this is what is we received in one case, right? Of course, if there is no target, remember we went through this. This is under hypothesis H1. This is very first thing we studied, right? And if there is no target, then you are in this ideal world, you will not receive anything. But in real world, this is what is going to happen. In real world, you are going to see. So this actually happens to be the same signal comes back, but together with the noise. And whereas this is, so both will look, if you look at the screen, both may look the same. Both, so which, here of course I can say, one is 0, one is a signal. So I'll say target is present. Looking at these two, what will you declare? Just looking at this, is this hypothesis true or, remember, you know what to do. Actually we haven't even studied this problem. I haven't told you how to, this will be next week, how to do this in continuous domain. What we have done is the discrete version of this. Remember, so we can form the joint density function, etc. But if the data, first of all, if the data happened to be in discrete form and you knew that it was all Gaussian, this and that, then you can form the likelihood ratio test and the etc. Right? We have gone through that. Now I'm going to take a slightly different approach and see how to address this problem. First of all, here the data is not discrete, it is continuous. Whether I should sample this data and bring it into this and solve it is unclear now. Whether we don't know whether then, because remember, generally by sampling you lose information. So I want to study this problem. I don't want, this we have studied earlier. Okay. So let me look at this problem. So one idea is that, remember, I'm not going to talk here about, so we have already done the likelihood ratio test, etc. And if you remember, there also, remember likelihood ratio test, f of, this we call Ri. Then you collect all the data, f of R under H1 over f of R given H0. You compare with the right, that turned out to be the optimum. Whereas here one idea is that, let me try to design a filter h of t or h of omega with the transform h of omega such that the signal component, I want to boost it. And I want to suppress the noise component. When the noise goes through this, I want to suppress. So I want the signal to be boosted and I want the noise to be suppress noise. Boost the signal. The philosophy is you boost the signal only at the decision instant. This is like saying that if you are going tomorrow evening to a restaurant, why do you want to dress up tonight and sleep? You get dress up tomorrow. So in other words, you boost the signal only when you are ready. Remember, I am not ready to make any decision here. I am not ready to make any decision here. For whatever reason, you have decided that I am going to make the decision at some time t equal to t0. Remember, you say, when you are ready, you come back to me, right? You go and ask somebody, people will say, why we discuss things in hypothetically. So this is when we will be ready. At that time, we want the signal to be boosted. We can say, why not boost here also at the other places? What is the point? Because remember, nothing is free. So if you keep boosting the signal here, this has to work harder, or it may be a more complicated filter. And anyway, that information is useless because you're only going to make the decision here. In communication, this is very relevant because each bit is going to come at T0, T0. So after the bit has come in, you make a decision at that time. So then you repeat it. So this is the philosophy. If you don't like the philosophy, you don't have to listen, or listen anyway, but you can always change the philosophy. I'm just trying to explain to you the ideas behind the motivation. Okay, so as I said, you may ask, what is special about T0? So I just explained to you. Think of this as one bit plus noise. So you may decide this as the end of that bit duration, so that you have collected the information about that bit, and then you want to make a decision. Then the next bit is coming. Then you will do the same thing and you will make a decision, and so on. Okay. We could also say that not only I want to boost the signal out, you can be greedy. You can say, I want to boost the signal at all time outputs. It's fine. It is fine, except this filter has to work very hard. And when you know this, if it works very hard, it may not be able to do the same good job here. It's possible. It's like, right? If you say, I want to be always in some tip shape, it takes much more work than if you only say between 5:30 and 8:30, it's easier, right? And if possibly we want to suppress the noise, where noise is slippery slopey, there is no good time for noise. So generally you want to suppress in some always or in some expected sense. In an average sense, okay? So remember, let me call the signal to be S of t and the noise to be N of t, and the output also will have two components, right? I think these are clear, right? This is the signal part, this is the noise part, right? So what is coming in R of t? So R of t is signal plus noise that goes through a filter H of t, and you get YST plus, let's say, I'll make it simpler notation for the noise. Here I used N, so I'm going to use W of t here, okay? You see, if you are saying this, this is the same as this, right? In another sense. We want to compress the pulse at the output. So that's our wish list. So far, we have just expressed the ideas. Now I'm going to express this into an express into a mathematical expression, right? Or a mathematical, convert this into symbols. So that's the hard part. This is also a hard part. Remember, for somebody with experience to sit around and visualize what I just said itself is hard, because you guys didn't think about this before, right? All right. So as I said, output needs to be compressed. Anybody knows what is this symbol, SNR? What does it stand for? Signal to noise ratio, which all you have heard. So anywhere you can put your finger and say, what is the signal to noise ratio? That means signal power divided by noise power. So by I mean the input to signal to noise ratio. Same thing at the output. You could say, what is the signal to noise ratio at somewhere. So this is input signal power over output signal power. I mean output noise, input noise power. Not. Anybody, how will you decide, how will you define these things? Now noise is a stochastic process, so how will you, a signal is ST, how will you design the signal or power or energy? Anyone? Signal. Signal is a waveform, there is no variance, it's a deterministic waveform. This may be your signal. There is nothing stochastic about it. This is the pulse you transmit, so maybe a sine omega naught t. Maybe the energy of the signal, which will be, as you said, the integral of the signal, right? That's one way. If you want to divide by t, then you will get the power, right? That's only a constant. So signal power or energy, whatever. If you like power, you divide it by t. If you like energy, it's not going to change anything. It's just a finite duration. How about the noise? Huh? What? Think. Noise is a stochastic process. So what do I mean by power? Anybody? What? All right, power spectrum is a function. I want a number. All right, so area under the power spectrum represents what? Anyone? Remember, there were in terms of symbol. So remember, this happens to be what? Yeah, what you said is true. This is the total power. This also happens to be what? R in Rn of? All right, so but that's going to be expected value of n of t, n star of t squared. So it is this, right? So that makes sense because if this is the voltage, this is the square of the voltage expected value. So what we want is that will be like the noise power. So this is what we mean by the input signal to noise ratio, okay? So to do all this, let's look at the output signal to noise ratio. So that's the output signal energy over output noise power. So for this purpose, it's actually, so that's one way you could define. Or energy or power, either way is fine. So remember, look at what I'm trying to do. I'm trying to bring this in. As I said, I don't want the output power, listen to me now. I don't want an output signal power based on a long duration. I just explained you the reason. Of course, then you can try to maximize it. If I'm going to make the decision around here, why would and I really don't care about other durations. This is where you want to increase the power. So what we could do is, with that sense, you take the output signal and put it like this. So you are taking the instantaneous value, and so one way you could define is that I'm going to integrate this over a small epsilon and divide by epsilon. So since epsilon is so small, very small, that's practically the same as the value instantly. So this is a peculiar way of looking at in communication you may not do this, you may again use an average signal power at the output. That is not what I am doing here. So one thing you can see is, this is how you bring in the compression property, saying that I want to, whole idea is that if you insist that the filter work on maintaining the value here high, naturally the other values has to be down because there is only so much signal is coming out. Everything you are trying to boost here, so hopefully these values will be down. These are indirect things which you have to conclude from what is going on. Whoever did this, it's a very mature, it's after years of maturity I see here. Because rather than try to do this also at the output, see that means I want to boost everything here and then I take an average value. That's not what we are doing there. Remember, conservation of energy, if this signal has some energy, even if it goes through the filter, the output thing only has so much energy. Now you are trying to boost everything at t equal to t naught. So if you are trying to boost everything at t equal to t naught, this black curve cannot come up here at other places because you are forcing the filter to act here. And so if all the energy is concentrated here at other places, it will take lower values. Again, if you feel you can improve this definition, do it by 13th. Or do it. How about the output noise power? That again we will use this definition, right? Look, that's the noise. Noise is noise is noise in the sense input is stochastic, so the output is another stochastic process. There is no way to, you can only talk about the noise minimization in some average sense. So this is where the things that we learned last week is going to be useful. This is as I said, some engineers years of very clever observations of what is required and how to bring it into mathematical formulation, etc. As I said, you may immediately object and say this is not the way signal to noise ratio should be defined. I agree with that. You can define it different way, as I did here. You see, generally it is defined as input signal power, which is you average over the whole duration of the signal. You can do at the output also, except you will get a different result. We want this property to come up. We want the pulse compression. All right, now what is the output? Remember, YST is YST. The signal part is, of course, the original signal convolved with h of t, right? So ys omega is the signal multiplied by h of omega. So from here, you can also write YST as the inverse transform of ys omega, right? So let me use this last expression. So this reads now 1 over 2 pi minus infinity to plus infinity s omega h omega e raised to j omega t naught d omega absolute value squared, right? Over what is this quantity? Anybody? Expected value of w of t squared is first of all RWW0, right? So that's the same as as you said, area under the power spectrum, SWW omega d omega. But look here, if the input is n of t and the output is w of t, what is the relation between the input-output spectrum? Same thing, right? So here I can write this as 1 over 2 pi, yes what? Yes? Right, S n omega h omega squared d omega. So this is the expression. What is unknown here? HW. So what do you want to do to this expression? Minimize it or maximize it? What do you want to do? Why? Why maximize? Because you want to boost the signal. Okay. So now by maximizing it, you are boosting the signal, and at the same time, hopefully, you are also minimizing the noise. Okay. So maximize it over the unknown, which is h of t or h of omega. Okay. Either way. So first, I am going to do the case where the input noise is white noise. So later we can do a colored noise case. So if the input noise is white noise, what is Sn and omega? Anyone? That's a sigma squared constant. So that constant goes outside, and so same limits, minus infinity to plus infinity. So this now reads 1 over 2 pi sigma squared minus infinity to plus infinity h omega s omega. I just rearranged it on the top. In the denominator you have minus infinity to plus infinity h omega squared d omega, right? I just pulled out the sigma squared outside, and you have it then. Okay. Then what? See, now the numerator looks like a omega, b omega, d omega. And anybody remembers this? We went through this.
Integral a square times integral b square.
Yeah, a omega absolute value squared d omega multiplied by b omega absolute value squared. This is known as Cauchy-Schwarz, right? Inequality, or Schwarz inequality. So you see, we can call this to be a of omega. This is a omega, and this is b omega. So the numerator is less than, so let me leave the constants there. Then the numerator is h omega squared d omega multiplied by s omega squared d omega over h omega squared d omega. Right. So what happens now? Anyone? Yeah, you see this term cancels off, right? H is gone. So there's something that we wanted to maximize is going to be less than or equal to 1 over sigma squared 1 over 2 pi minus infinity to plus infinity s omega squared d omega. What is this quantity? Anybody? That's the same as integral 0 to t st squared dt by Parseval's theorem. Right? That's the energy of the signal over sigma squared. So this happens to be the signal to noise, the actual signal to, or we can simply call it ES, E over a naught or whatever. So here comes the punchline. Remember, when will you have equality here? Generally, this quantity is less than or equal to this. When will you have equality here? When A equal to B star. Okay. When A omega equals B star. Remember, complex quantity. When A equal to B star, this becomes absolute value of A squared, right? And remember, this becomes, these two become equal. And you get the same, you get everything matches out, right? So this is equality. Equality if and only if necessary and sufficient, you need A equal to B star. So look, here is the punchline. Look at this. You want to maximize this output signal to noise ratio. Output, that is this expression. This expression, look at here. This expression is less than or equal to, you have only less than or equal to this quantity. Look at the final quantity, it is independent of H. This is a constant. So the best you can do, what is the maximum value of this quantity? Anyone? What is the maximum you can drive this to? ES over N naught. That's the maximum value. So you conclude that SNR output maximum is going to be ES over N0, and we can. And when will you realize that? What is the condition for when you will realize this? When A equal to B star, right? A is this, B is this. A is what we are looking for. So we'll get the condition for the filter. When H of omega is B star, that's S star omega e raised to minus j omega t naught. So now again, if you have done the transform, what is this in time domain? Anyone? Hello? So what is the expression? S of? Actually, you have to do this. This is like. Why is that? I think I showed you this. Take the transform of this, you will get this back. So you see the interesting thing, we started with S of t. Look here. We started with S of t and noise. Now we are saying this filter has something to do with S of t. It's not surprising, right? You cannot design a filter neglecting the input signal. So these kind of systems are known as adaptive systems. You can say the answer is a low pass signal. You pass through a low pass filter, it will all get compressed. That's nonsense. So the filter here depends. So the filter is H of omega or H of t. It depends on the signal you are transmitting. And both in communication and radar, you do know the signal. So you see the unknown, this was unknown. So the unknown quantity is matched to the signal. That's why this filter is called a matched filter, okay? So it goes like this. I'll draw some diagrams. So of course, if you have a rectangular signal coming in, then match, so what is the match filter? Anybody? All right, so you flip it. So this is your S of t. So when you flip it, you get S of minus t. Then what? All right, then you have to shift it by what amount? So you are going to make the decision at t equal to t naught. So depending on t naught, so I'll draw 2-3 cases. So this is t. Let's say I decide that decision will be made at t by 2. Decision will be made at t. Decision is going to be made at 2t, okay, for example. So if you make the decision, then this is S of minus t. If you shift it by t by 2, it will look like this, right? This is the match filter in one case, because you shifted S of this by t by 2 only, right? Here so here how will it look like? Yeah, so here it will look like this because you're shifting it by t. Here it will look like this, right? And how will the output look like? So now you have to convolve this with this. So see, the output is going to look like this, right? So you see, this has been compressed. But you say, is this all you can do? Can you do better? So this is where it opens up, okay?
Add another match filter following?
What do you mean? Add another match filter? Well, why would, first of all, Remember, if you, first of all, you should look, if you have two serial filters, you might as well, you should have been able to design it as one filter, isn't it? No, I'm saying, if you could do it in stages, you can do it together because everything is linear here, right? So, whatever you can do it in one stage. First of all, you see, you have to pay attention to this. What will be this width? Anybody?
2T.
Yeah, because if you convolve this with this, this with that thing, you are going to get 2T. So here, it looks like you have actually made it worse. It has become longer, but you have to work out the details. The amplitude might have increased it, but the pulse has become of this shape. So you can say this is not a good compression. So that's why I give you two, three signals. So it's going to depend on the nature of the input signal, how the output looks like. Because in some cases you may be able to get something like this. See here also, remember, anything convolved with anything is going to be of duration double the length, right? But the question is, how do you control the side lobes? Here you have no control of the side lobes. If you put another filter, it's only going to get worse. See, generally, if you have a signal like this, you pass it through a h of t, and this is duration t1, this is duration t2, what will be the output look like? Whatever it is going to be duration t1 plus t2, right? So it will look like this in general. So this actually is going the wrong way. You're not compressing, you're actually decompressing. We want it to go this way. So the only way is this thing has to work in such a manner that the side lobes need to be minimized for the compression to happen. So how is the side lobe minimizing? Here it's only as powerful as this. So here we are forcing the output to go, we are forcing the signal to be peak at here. The signal is peaking, you see. Signal is peaking as you want it. What is not being worked out is this is not going down as fast as you would like. So you can see its limitations. It's doing what you have wanted it to do, which is peak value here, but the other values are dying out very you would like it to die like this. That's not happening here because a triangle is like this, right? So, but if you can, so remember, triangle goes like this. This is the output if you convolve a rectangular with rectangular. But if you convolve some other pulse with its match filter, you may get like this. Then we'll say that this pulse is better than this one. And that's where I want you to do some work, even if you do it by trial and error. For example, look at 3 problems I give you. I mean, these are not easy problems. Yeah. So again, if you want to, anybody wants to spend some time and yeah, you are right. In the complex case, there is a conjugate, right? Thank you. So what she is saying is, this is just a Fourier transform stuff. This is the right answer. Because let's take the Fourier transform of S naught T naught minus T. So that's integral from minus infinity to plus infinity, right? S naught T naught minus T e raised to minus j omega t dt, right? So let me make this to be x. So this is S star of x e raised to minus j omega naught. Remember, x is t naught minus t, so t is t naught minus x, right? T naught minus x. So dt is minus dx, so minus dx. When t is minus infinity, this is plus infinity. This is minus infinity. Because of the minus, the limits will change back, right? And we can actually pull out. So this is now S star of x e raised to plus j omega naught x dx multiplied by e raised to minus j omega naught t naught, omega t. Right. There is no omega naught here. But you see, I'm going to pull a star outside. So e raised, I can write this as right. See here, e raised to minus j omega t naught. I pull that outside, right? Then once I pull this outside, this overroots minus infinity to plus infinity s of t e raised to minus j omega t dt. I change x to t, but this is s of omega, so it's s star of omega e raised to. We get this transform back. So she is right, you need a star here, but if it's a real signal, it doesn't make any difference. Okay, very good. So you can, this is the challenge, you can go and generate any signal you like. But I want the output to be, and use the match filter as the compressor and see how much compression you get. So one signal I write is so you take a sinusoid, okay. So remember what is this? This you can say this is a sinusoid over a pulse, right? So call this S of t. So this is, let's say, cos omega naught t, a t over some duration. Then you generate its match filter. You know how to generate it. H of t will be, since this is a real signal, S of t naught minus t. Take t naught to be t itself. So, okay, so you flip it and shift it. Then the output is going to look like what? Anyone? How will the output look? You can draw it, so it will look like this, I think. Right? So you see again, as I said, it's peaks here, but the compression is very poor. Now suppose you bring in this signal. Anybody knows what is this signal known as? Anybody? This one. Let me call it S2 of t. Huh? So this has a sinusoidal component, but it also has a quadratic phase. So it's if you call this to be the instantaneous phase. See, the derivative of the phase gives you the instantaneous frequency, right? So in
It's not a chirp.
yeah, it is a chirp, right? So this is omega naught t plus beta t squared. So its derivative is going to be omega naught plus 2 beta t. So if you plot the frequency, instantaneous frequency, it goes like this. It's called a linear frequency modulation, and because the frequency changes with respect to time. So this is omega t. Omega has a constant, so it actually builds up a little later. So it's like this. It has a constant, and then it has a linear component, right? So what is the big deal? So of course, if you plot it, it will look like the initially the frequency is going to be faster and faster. So it is right. This is the way chirp. Now it's interesting. It has been studied in detail. I'm saying here, of course, this will also start like a sinusoidal concept, but its frequencies will increase. So you plot it and it is constant modulus. Interestingly, I don't want to go through all this. The output will look, compared to this, it has got excellent compression properties. Why so? So maybe you can look into this. If you want some information, it is there in my book called Waveform Diversity. I'm not going to go through all this now. I just wanted to give you that from here onwards, you're already on the highway. By which I mean it's up to you. You can spend some time and read up and learn about any topics. You do have the background. And there is so much on everything that, remember, 4 plus 3 is 7. There is a clear answer. Things like this, there is no end to it. There is, here, the book is called Waveform Diversity, Designing Waveforms. And there is a subsection here on pulse compression. Section 2.3 is on chirp signal and pulse compression. So of course you have to read it and there is some logic why this happens. But even better, I think till today there is no pulse, no signal which has got better pulse compression properties. So this is why I said, first, one way to get warmed up to this is you take the chirp signal, you just design it match filter, and simply plot it. You yourself can see the pulse compression properties. Then you can think about why this is true, have some applications, this, etc. You take any other signal and pass it through it, you are going to see this phenomenon. The pulse is going to spread out. It makes sense, right? Look, after all, you are convolving a signal with another signal. This signal should have it will look worse. Whereas here, everything is the opposite. See, you're convolving a long signal with a long signal, but it looks like that's because the side lobes have been suppressed. Why? That's what I'm saying. You have to dig in some amount. Even this, I mean, you can figure out how low is the side lobe. Is it 10 dB, 15 dB? What is the role of this beta? Of course, the role of the beta you can see. The trouble here is if you transmit you can see that this is, I'll tell you this much. This is inversely proportional to the bandwidth, but the trouble with the bandwidth is, look at here. If you transmit for TT, this bandwidth is going to be 2 beta T, which you can see from here. This is the instantaneous bandwidth. If T goes from 0 to 2T, this will increase. So the larger you wait, the more so there is no free lunch or free dinner, either way. So if you wait long enough, of course you will get a compressed pulse, but you are also using up a lot of bandwidth in the beginning. So this is one of the homeworks for you to plot it. Remember, the filter is match filter. But now if you say you can design a better filter, that's fine also. So as I said, this is an open topic. And so the question is, so in pulse compression, this is still an open question. What is the best input? Of course, you have to word the problem correctly. Hello, what is the problem? You have a pulse of duration. You remember, you cannot compare apple and oranges, even though you can. But it should be a pulse of duration T and a certain amplitude, preferably constant envelope. And it uses certain bandwidth. Bandwidth also is, okay. So a certain duration and certain bandwidth. Give me the filter and tell me how much compression can you get. Can you do anything better than a chirp? If you cannot do anything better than a chirp, you better keep quiet because chirp is already doing a certain amount of job. So this is a billion, B, B as in boy, billion-dollar industry in radar. Radars use Chirp universally because of this, one reason being this. And but this is still a very meaningful problem. How do you design excellent pulse compression filters? So far the answer is we use the match filter. Now, you may poo-poo match filter. Again, match filter, as I said, is very robust. And again, it is that B as in boy, billion-dollar industry. Match filter is universally used to do the pulse compression. So you can do this. By the way, I did solve the homework solutions. Unfortunately, I left it at home. So I'm either going to PDF it and send it to you, or I'll bring it next week. But this you can, so you're only going to answer the first question at this point by plotting it. Now, if I miss some parameters, you make up some parameters, okay? For example, I didn't specify, for you to do the MATLAB, you need to fix the values. So you fix up omega not something and beta equal to something, etc. So then you will see that if look at here, both are pulses. This is a constant envelope at some frequency. This is constant envelope starting at same frequency for same duration, different bandwidths of course, but the output looks like this. So naturally you will go for this rather than this. So that's the reason I'm saying. And here of course the filter being used is match filter. Here, of course, you have to do some reading. I only gave you the final result. Why all this is, as I said, it takes some time. I cannot do it in 5 minutes or 10 minutes. So the first, that's why I gave you the second example, second exercise. What is the transform of this signal? Again, this has been solved for, I think now at least 100 years. I also have the result in my book. And I think the book is also, somebody has put it on the web. So, but this is a standard. You can look into Papole's Fourier transform book. And you should know the, anybody knows what is the transform of this?
Delta
Very good. So what is in the frequency domain? It's now how about this? So you can go home and do, this is what I wanted to write as homework number 3. Again, all these are done. Suppose it is, so a complex chirp. And so I want you to find the transform of this and plot it. Okay? So if this is f2 of t, I want you to find this out. Again, you don't have to do much, you don't have to do any original invention because it's all, you just have to copy it from somewhere, right? So again, I have an appendix here where it is done in detail section. So transform of a chirp signal, page 59, you can pass this around. I'm not advertising my book, but it just happens to be there, okay. And the book is called Waveform Diversity. So my point is, these things you should know. The result will turn out to be something like this. That's the interesting thing. So you need to figure out what these values are. So look at this, it's approximately constant. So the chirp apparently has everything going, it's like a God-given signal. Constant modulus, so it's for a, even you can implement it at microwave frequencies. And look at here, if you transmit it for a long time at very low power, look at here, the output, as I said, output is inversely proportional to bandwidth. So by keeping it over a long time, you're increasing the bandwidth. that will make the pulse compress better and better. And this amplitude, I believe, is also proportional to the bandwidth value. Where is problem number 2? What did I say? What is the amplitude? Amplitude is pi over beta. Amplitude of the output spectrum. So again, it's all there in the book. I don't remember the value, but the whole idea is that even if you keep this input inside, which is what you want, where you transmit, you keep it low power, but the output will, through the compression, you pick it up. Without the compressor, the whole technology is dead, right? Otherwise, you are transmitting this over a long time. It comes back from everywhere. How will you figure it out? Whereas here, if you have multiple targets, the output is going to look like this. All in this duration. So this I can see the multiple targets. I can hopefully see their strength and this and that. Again, at some point we had a course on the waveform design, but so there are other stuff we can do. But let me, anybody is interested in communications here? Hello? Yeah, so for your sake, I will give you a little more application of this into waveform design. Any questions so far? I do have a couple more topics that I need to go over, but let me do the colored noise here. The same thing, remember we did this for white noise, right? So the original expression was, if you remember, 1 over 2 pi you had h omega squared, but you also had Sn and omega d omega. Suppose this is colored noise. That means Sn and omega is like this. So remember, this is the SNR output. So let me, to solve that problem, remember, so you cannot pull this outside, right? Hey, you're playing with phone now? Searching for that, you do it later. You listen, then you ask me the question, you listen to me here. So you have noise here, I pass it through a filter, you get output noise. One more time, what is output power spectrum? Anyone? Input power spectrum? Yeah, magnitude of g omega squared. Okay. So this is a problem. I want to, I have colored noise here. I want to design a filter to make the output look like white noise. So this is called whitening filter. So now you know the answer is here. Look at here. What do you want here? You want this to be 1, right? Let's say you white noise. So it already tells you that the filter has this property. The question is, how do you design g omega? Okay, so let me show you some. So suppose you can, and you also, of course, you also want me have this filter to be stable and so on. Okay. Remember, g omega is not 1 over Sn and omega. G omega absolute value squared is 1 over Sn and omega. Okay. So this problem comes under something called spectral factorization problem. The inverse problem is the following. Suppose this is white noise with the power spectral density 1, and I pass it through a filter and I get some noise W of t. What is the power spectral density of SW omega? Anyone? So that's simply magnitude of h omega squared, right? So this is the problem. Can you read it from there? You? Yeah. Remember, listen to me what I'm saying. If you are given this filter, it is easy to find the power spectrum, right? Because as you said, the power spectrum is simply the system squared. Think of the converse problem, which is always hard. I give you a power spectrum. I want you to put it like this. What I'm trying to say, I want to conceptualize a filter which is driven by white noise. That's the problem here. Given any power spectrum, of course the power spectrum has this property, how to find the system corresponding to underlying system. So suppose you have a black box here. To find out what is in the black box, we can do this experiment. You excite it with white noise, you look at the measurements. From that, suppose you can compute the spectrum. The question is, you know the relation between the spectrum and the system. It is this. So if I give you the spectrum, how do you find the system? What do? Answer is not square root, because you want h of omega or h of t. This is only going to give you absolute value of h of omega. So the phase is not known. So this is called the spectral factorization problem. Again, you can read up. It is not easy, but I'll give you the some ideas in the rational case. And I don't know, maybe if there is a time on 13th, we may, that also is a course by itself, spectral factorization. Again, I used to teach all this. What is happening is now I don't see the students. No students, no teaching. Say, look at this spectrum. You can check that's a spectrum, right? So these are called rational spectrum because everything is in terms of rational functions of omega. Of course, the same problem suppose I write it like this. This is also a spectrum, but trying to write this like this is the $24 problem. So the other one is easy, so I'm not going, this is the real challenging problem. If you write an arbitrary function which is non-negative, how do you find the system behind it so that I can write it like this? How do you find h? So here the argument, see this cannot be a spectrum, right? What is the reason? This cannot be a spectrum. What is the reason? It could go negative. So if you have a term like this, it has to be of this form, right? For some, I mean, you can of course have some term here. You don't need to. So we want to write this as h j omega squared, right? So question is what is h? So as you know, in the complex domain, omega is this is j omega, this is sigma. So and s is sigma plus j omega. So we are really plotting this in the j omega axis. So another way to write this would be h of s multiplied by h of minus s at s equal to j omega, right? Right, that's the same thing, right? S equal to j omega h of s. Okay, so s equal to j omega is the same as s squared equal to minus omega squared, or omega squared is minus s squared. So another thing, so immediately what we are going to do is I'm going to write this in terms of s to do this factorization. Okay. Now remember, another thing also, this cannot be a spectrum. What is the reason? This cannot be a spectrum. Huh? Go negative, right? So very quickly you can see that if the spectrum is rational, it has to be functions of omega squared. Agreed? As I said, so all omega squared or omega 4, etc. If there are negative terms involving like this, that has to be some even power, right? This cannot be odd power because otherwise at some point this will go negative. So the spectrum being s equal to j omega, I'm going to rewrite this in this fashion so that, and this I want to write, spectral factorization is right, I want to write in this fashion, right? H of s. That's the same as saying I want this to be written as h of j omega multiplied by its absolute value squared. So what is known here is this, what is unknown is this. Generally this is known, this is unknown. This of course that's easy. So coming this way is hard, but this will give you some idea. So let me plot these are the zeros, these are the poles. So let's plot all the zeros. I'm sorry, so let me rewrite this as, this is in terms of s squared. Remember, omega squared is s minus s squared. So omega 4 is s4, so this is 1 plus s4. Omega squared is minus s squared, so this is 2 minus s squared. And this is 3 plus s squared, the whole squared. Let's say 2. And I want to write this as h of s and multiplied by h of minus s. We certainly want this filter to be stable. That means all its poles should be where? Yeah, poles, if it is a discrete left half plane, if it is the discrete domain, it should be all unit circle in thin. And the zeros, there are no restrictions generally, right? But let's say that we will also, you'll see the reason soon. suppose we make the restriction that we also want the zeros to be in the left half plane. You can put them anywhere, but for the time being, poles in the left half plane, zeros in the left half. So let's plot the poles and zeros. Where are the zeros here? This can be factorized as what? 2 plus s multiplied by 2 minus s, right? So 2 plus s is s equal to minus 2, right? Yeah. 2 plus square root of s, right? So the 0 I'm going to use as 0, pole I'll use it. So this is minus square root of 2 plus square root of 2. So I have s plus square root of 2 one term. And remember h of s, the other one is minus s plus square root of 2, right? Here where is the 0? S equal to j square root of 3 omega and 1 at minus j3 omega 3, right? Omega equal to, so s equal to square root of square root of 3 j multiplied by square root of 3. And but you see, look here, this appears 2 times, right? And this also appears 2 times. So if I take one from here and one from here and put it here, one from here and one from here, put it here, that's the same as 3 plus s squared, isn't it? There is no harm. Because look, I change s to minus s, I have it here. S to minus s, these two are the same. Okay. Denominator is a little crazy, so you want to solve s4 equal to minus 1. Minus 1 is what? E raised to j pi. So that can be written as 2m plus 1 pi, right? So the 4 roots are, Sm will be e raised to j pi 2m plus 1 over 4. So where is the first root? Put m equal to 0. So the first root is e raised to j pi over 4. So in the unit circle, easy to plot. So which I will draw it here. The unit circle is going to be inside, right? So where are they? One root is here, right? I mean, this is a pole now. Another one here, another one here, another one here, right? Because you put m equal to 1 through 4, you get the m equal to 0 through 3, you get the 4 poles. So one pole here, another pole here. So so this is e raised to j, look at here, put m equal to 0, e raised to j pi by 4, right? That is cos pi by 4, how much is it? 1 over? So this is 1 plus j by square root of 2, right? So this is 1 minus j by square root of 2. So this is minus 1 plus j over square root of 2. This is minus of 1 plus j over square root of 2, right? So let me call these roots to be S1, S2, S3. I mean, this is S0, S1, S2, S3. Okay, 4 roots, right? Look here, I can take any 2 roots into the left side, or remember, so this is, I can take this to the left side or this to the left side. If you want stability, we better take this to the left side. So this should be S minus S1 and S minus S2, isn't it? This is S1, S2. And this is the remaining stuff, S minus S0, S minus S3. Now you can simplify S minus S1. So S minus S1 multiplied by S minus S2, this is S plus 1 over square root of 2 minus j by square root of 2, right? Then S plus 1 over square root of 2 plus j square root of 2. So this is S plus square root of 2, the whole squared plus half. And if you expand that, you get s squared plus square root of 2s plus 1. This is the second order Butterworth filter, if you realize. So I'm multiplying, so I can replace this by here as s squared plus square root of 2s plus 1. And this happens to be, if you do all this, this will turn out to be this. So you see, this must be my h of s. And if you replace s by minus s, this is my minus s. So I found the filter. This is called the spectral factorization, okay? Advantage is, look at here, this filter by design is stable because all the poles are in the left side. And its zeros happens to be what? Also in the left side. Why is this useful? Look here. So this is how you do the spectral factorization. So remember, the problem is, given a power spectrum, find this system. But look here, given a power spectrum, here also you want to find a system, but the power spectrum is flipped. Or another way to say it is that you can also write this relation the other way, right? Here the g omega is what you are looking for. The whitening filter has the property that 1 over g omega equal to, you want this filter also to be stable. Or other way to look at this is, for a system, maybe easier way is this way. For any spectrum there is a system. Not having a desk here is so crazy. I just went through this. Look here. I just went through this. Remember, any power spectrum, the other way. For any power spectrum, I can find a system, right? That's what we found. We just did it, h omega squared, right? So if I plug this in here, this reads now 1 over h omega squared, right? Suppose I found the h of s, then what is the connection between g of s and h of s? Anybody? Look at here. G omega, this is g j omega, this is h j omega. So what is? So I know this filter because I just found out this filter. Yeah, of course. Why so hard? So the whitening filter is 1 over the innovations filter. You want this also to be stable, right? Well, look, the zeros of this become the poles of this, right? So if you want this to be stable, you better have the h of s, all the zeros in the left half plane. So, right? So not only you want hs to be stable, you want its inverse to be stable. You want this to be stable, and you want its inverse to be, you want this to be stable. That means for the h of, if you want these two conditions, both its poles and zeros must be in the left half plane. So that's the reason by design we can do it, you do it. So what is my point now? My point is, if you want a whitening filter, this is what we will do. Whitening, you find the spectrum, you do this job first, you find the stable, you find the spectral factor and flip it. This spectral factor also is known as, so look at this one. Suppose I have a spectrum. Now this is also known as the Wiener filter, the factor of, so if you have, this is a simple spectrum, right? I want to write this as h of s multiplied by h of minus s. Remember, so the first step is replace omega by s. omega squared by s squared. So this is 2 minus s squared over 1 minus s squared the whole squared. So you can factor this as square root of 2 plus s multiplied by square root of 2 minus s, and 1 plus s squared 1 minus s squared, right? Right? Because this is my h of s, then if I replace s by minus s, I should get this. So everything is good. But you see now if I take 1 over h of, this is stable. By design this is stable, right? This h of s is stable. Now if I look at 1 over h of s, that's 1 plus s the whole squared over square root of 2 plus s. Its pole is also on the left side. So this is also stable. So that's the filter we want here. This is your 1 over g of omega. So if you put the flipped version of h, this will turn out to be white noise, right? So, hello, look at what should I do first? See, I have a signal coming in, but the signal is coming in colored noise. So what could we do first? First, if you want, you can use a whitening filter conceptually, okay? Then what is coming in is the signal is originally ST. Because you used a filter here, the signal changes to something else, FT. FT plus white noise. Then what do you do? This is how do you compress this signal? But you just use a match filter, right? Which is going to be f of t naught minus t. So you can say, so this is again a very classic solution. When you have colored noise, first you can do the whitening filter, then you do whatever is appropriate for the white noise. So whitening followed by match filter, whitening followed by match filter. This you are going to hear again and again if you go to the right place. Right? So many ways you can do it. Remember, I left it here. So you can say that I will whiten it. If I whiten it, remember, this will become f of omega. And there will be nothing here because this has been whitened already. Right? Because what is coming in is, so what will be the filter here? This will be, the appropriate filter will be f dot of t naught minus t. So that's what you should do it here. And what is f of t? F of t is going to be g of t convolved with s of t. How will you find g of t? You have to go through the spectral factorization. We just did it, right, for an example. What is Sn and omega? Of course, it depends on this colored noise, n of t. Yes? You? Is okay or no? You seem to be in doubt. You are tired, I should be tired.
Excuse me, Professor, generally white noise is of infinite energy.
Right.
But here we are making white noise.
Well, so, right, so the idea is if you live that long, the output will be, remember conceptually it is fine, right? So we are saying that we want the output power spectrum to be like this. So if you give me an input power, so the question is only certain things, there are some conditions. The question is, when can you do it? So you do need to do some reading. See, for example, if the input is like this, suppose this input spectrum is like this wouldn't make any sense, because when you invert it, it is going to blow up, isn't it? So the condition is, to answer your question, or the right question is, when can you find a spectral factor? You need to have the so-called, maybe you have heard the term, Paley-Wiener criterion to be satisfied. In other words, if I remember, it is for at least discrete spectra, you need this condition to be satisfied. And for continuous spectra, it's something like Paley-Wiener criterion. So in other words, if the power spectrum goes to 0 somewhere, then it cannot be factorized. You will not be able to find a filter which will do this job, complete whitening. But for example, if a power spectrum, input power spectrum is like this, you can certainly find a filter which will convert it. What you are saying is that if I wait long enough and add all the energy, of course it blows up. But if I look in any tiny duration, it's not going to blow up. If you have the means and tools and the time to integrate it from minus infinity to plus infinity, it will blow up. But at least that's the way conceptually. But the question is, under what condition can you convert an input? So an input spectrum is like this, you cannot convert it into this. You cannot, or there is no, because you cannot whiten it. So the whitening condition is that generally the Paley-Wiener criterion should be some conditions. I'm more or less sure this is right, but you can check the Papoli's book. You can actually put these two things together, but this is a neat idea. When the noise is colored, provided the colored noise, so I should have added this, provided the colored noise spectrum can be factorized, then you can use the inverse of that filter to do the whitening job. Once you're whitening, remember, you're only whitening the noise, you are not whitening the signal. So signal, unfortunately, the signal is going to get transformed. But a new signal plus white noise, then you just use the match filter, not for this. Match filter matched to this. So a match filter together with the coupled filter, the concatenation of whitening followed by match filter. So in practical waveforms, a lot of places, this is not noise, because of this is such a mess, you assume the noise to be white and get it done with the white noise and run, right? But if you have reasons to believe you need to do this, then you need to do it. All right, there are a lot of topics to be covered. Let me do one important topic because it's important, and also some application I wanted to talk to you. There is more we can talk on this, but I'm going to sort of, because we only have essentially this week and next week, because I need to give you at least 1 week to study. I mean, 13th I will talk about certain things for about 1 hour. Then you can do the presentation. Let's take a couple of minutes break and then let me talk about a concept called ergodicity. So, say hello. If you're tired, drink some water and come. So this is going to deal with estimating these quantities. Okay. How do you estimate the mean in reality? Okay. So of course the assumption is you have a stochastic process has various realizations, and so if you fix a t to be t naught, you want to do expected value of t naught. So you remember this is a random variable here. Hello, this is a random variable, and you have a density function here along this direction. You multiply for every particular t naught, it's a random variable. So there is conceptually there is a density function. You multiply that. You may, what I'm trying to say here is, you may get it to be a function of t naught, or you may get it to be a constant. Okay. This constant doesn't mean it is stationary. It is only Whiteson stationary, right? In both the cases, what is the bottleneck? Usually this function is not known. Nobody knows the density. What do you have in average? You go and make a measurement. At the best, what you have is one of these realizations. I think generally the data is, I'm going to project it here. One of these realizations is available. Okay, this is all you have. So you see, to do any one of them, remember even autocorrelation function is see, it's an expected value. This means a double integral x1, x2, f of x1, x2, first time, second time, etc. Right. So again, this density function need to be known. So as I said, generally these density functions are not known. This is a case where the mean is not constant. This is a case where the mean is constant. In both the cases, the same problem. You need to do the averaging in this direction. But generally you don't have all this data. You go and make a measurement. Where are the wireless guys? They make one measurement, right? One set of measurements. So you just, measurement is against time, right? So of course I'm going to denote it like this. So all the other things are missing. Of course many people can stand at the same time and do it. So that's one way to do. But suppose you only have one time shot. And then what you could say is that this is truly like apple and orange. Instead of doing the averaging in this direction, can I substitute it with an average in this direction? This is time average. In other words, can I do this? Of course you can do it, you'll get something. The question is, will this quantity, how close will it be to this? So look at this, how ridiculous the question is. We really should be doing the average in this direction, which is over various realizations, right? But this is impractical because we don't have the data. What we have, the data is one realization. So the question is, can I do a time average to replace an ensemble average? Right? So completely different things. So that's why it's a, so when will it make sense? Hello, look at this. Whenever you do the time average, you are going to get a number. Here, look at it. The mean value is what? Here. Mean value depends on T0. So if the mean value is not a function of time, the comparison doesn't make any sense because the mean value will depend on which time you are measuring. But the only place it may make sense is here. If the mean happens to be a constant, there is a chance that, so the question to ask is, when will this quantity go to the mean? Under what conditions? Okay. So remember, this is a number, but this is a random variable because here you are just averaging many random variables. Let me put here 1 over 2t also. I'm doing a truly time average. And in the discrete case, it's like this. Right? This is what you do. We do this all the time, but the question is how valid is it? That's what we are going to. So remember, as I said, you can see, this is no comparison to this. Nevertheless, we are forced to ask whether an ensemble average, what is written here is ensemble averaging over various realizations using its proper density function. In that value here, can this be substituted by this? See, this is an unknown constant, right? So what we are asking is, when can a random variable begin to look like a constant? What is the condition? When can a random variable begin to look like a constant? What? A random variable, when will it begin to look like a constant? What? Remember, simple question. There is no process here. A random variable. 630.
Variance tends to be 0.
Right, so that's, and one more condition. A random variable has a density function, right? This is x. If the random variable needs to look like a constant, what will be the nature of the density function? It should be, so you could say that the expected value of the random variable, of course, is b, and the variance of the random variable should tend to 0, right? So that it begins to look like a constant. So we want these conditions. We want the expected value of this quantity to be whatever is that constant, right? So in this case, we want the random variable to look like this constant. Again, before I even state that, this problem makes sense only if the process is what? You don't need Whitening stationary, at least you need stationarity in the mean Whitening, okay? So, Whitening stationarity so the mean need to be constant, right? That's all I'm saying. That's the starting point. If mean is constant under this extra condition, the extra condition is that the variance of mu hat should go to 0. So let's compute the variance of mu hat. Variance of mu hat is expected value of mu hat minus mu the whole squared, right? So what does that mean? That means, so mu hat minus mu, of course, is, I can write it like this, right? Isn't it right? Because you two integrals, you again get the same thing, right? I mean, you can check expected, this is true, right? Because expected value of mu hat is what? Expected value of minus t to t, 1 over 2t, x of t dt. This is the same as 1 over 2t minus t to t, expected value of x of t dt. What is expected value of x of t? Remember, that's the assumption we made. We need this to be a constant, so that's mu. So the answer will turn out to be a mu 2t over 2t, so that's good. So let's do variance of 2t. That quantity should go down to 0. Right, so this is mu, that's fine. So variance of mu hat is expected value of mu hat minus mu the whole squared. So here I can substitute that integral twice. So this is two integrals, right? Minus t to t, minus t to t. So this is xt1 minus mu dt1. This is xt2 minus mu dt2. 1 over 4t squared outside, right? 1 over 2t, 1 over 2t. So squared. So this now reads 1 over 4t squared, double integral minus t to t, t to t. Then what? When you expand this, what do you get? Expected value of xt1, xt2 minus, you go through all this. Anybody can do it in their head? There will be 4 terms, right? Second term is mu multiplied by expected value of this, which is mu squared. So 2 minus mu squared and plus mu squared. Okay, so you'll get this, right? Yes? Because it's getting late. But you see now so we want this expression to go to 0, and generally we will like this assume. Now let's assume, suppose the process happens to be Whiteson stationary. So what happens to this expression? Anybody? Rxx t1 minus t2, right? So this is 4t squared minus t to t minus t to t. This is Rxx t1 minus t2 minus mu squared dt1 dt2. We went through this before. We need to do the integration inside this, but only along this line, right? This line is t1 minus t2 equal to tau. So let me define t1 minus t2 to be tau. Then remember, we made a small displacement. We found out this happens to be 2t minus tau, right? Multiplied by d tau, right? So this integral, of course, can be written as 4t squared. One integral, right? What are the limits? This goes from minus 2t to plus 2t. Okay. Minus 2t to plus 2t. Rxx tau minus mu squared. This is, of course, the covariance. So if you want, you can call it cxx tau. Multiplied by what? The area of that, right? So that is 2t minus tau d tau. So let me take a 2t there. So this quantity I'm going to write, this is 1 over 2t minus 2t to 2t cxx tau multiplied by 1 minus tau over 2t d tau. Should go to what? If this quantity goes to 0, then what happens? Hello? If this quantity, suppose it goes to 0, then what happens? This behaves like this, and this becomes true. So that means that quantity converges to this in probability 1, or mean squared convergence. And here in this case, apples and oranges can be compared, because one is averaging in time. Actually, we wanted averaging in ensemble. Both are, so this is very special. Just because the process is Whiteson stationary doesn't mean this makes sense. You need an additional condition. So ergodicity is a deeper concept. You say, what you are saying by ergodicity is that an averaging which should be done in this dimension can be replaced by in the time domain. Time domain data of any one sample realization actually has all information as good as doing various experiments. Very special case, but you need it to use it all the time. So when you are using an average like this and saying this is my sample mean, you are actually saying that this quantity I can replace it with this. But you do need an additional condition. The condition is this. So the necessary and sufficient condition for a process to be mean, if this is true, then you call the process to be mean ergodic. So this is mean ergodicity. So first of all, x of t need to have constant mean. Then mu hat, which is 1 over 2t, which is based on one realization, x of t dt, tends to the unknown mean mu, if and only if this expression, 1 over minus 2t to 2t, cxxx tau, 1 minus tau over 2t d tau goes to 0. This is the variance of mu hat. This is of course under the additional assumption that the process is also Whiteson stationary. So is this always true? Hello, is this always true? Maybe, maybe not. In some processes this will be true, some processes this will not be true. So if this condition is not true, then the process is not mean ergodic. So let me show you a case where this is true. Anybody knows the difference between a function is integrable and it is absolutely integrable? Anybody? So C of tau, what do you mean by integrable? So if this quantity is true, we say C tau is integrable. What is absolute integrable?
Integral with absolute value is bounded.
Which condition is stronger? Anybody? By which I mean if let me call this 1 and 2. If 1 is true, is 2 true? Or 2 is true, 1 is true? Which one is stronger?
2 is true, 2 is true.
You are murmuring, I didn't hear you. Well, if this is true, this is true. If this is true, this need not be true. So this is a stronger condition. Yeah, well, you can just use, look, this is always true, right? So if I take the absolute value outside, this is true, right? Yes? Why? You are again agreeing with everything. Why is this true? Isn't this true? If I have a plus b less than or equal to, why is this true? So you have worked, yeah, whatever. So once you convince this, so you see, if this is true, this is true. This is true, this is 1. But if this is true, this may not be true. Okay. I mean, suppose this is, so if this is less than infinity, this is definitely less than infinity. Okay. All right, so when is a process mean squared periodic? Let me give you a theorem. Or a result. If the autocorrelation function is absolutely integrable, in other words, if this condition is true, all these pens are bad. Not mean square periodic, is mean ergodic. Okay, so you understand the theorem? If this condition happens to be true, so this is a strong condition. If this is true, then the process actually has this desirable property. I am going to prove it for you right now. Right? This is what we need to show, right? But variance of mu hat, actually we have an expression. It's here, right? I'm just copying this expression. Remember, it variance being a positive, let me take absolute value. That's fine, right? No change. But this is now less than or equal to, absolute value of an integral is less than or equal to what? Right, so 1 over 2t integral absolute value of cxx tau multiplied by absolute value of this quantity. I don't need absolute value. Why is that? Because this is already positive, so I don't have to put, I just need to put. So this is certainly true. What is the value of this? Anybody? For any tau, what is the value of this? Look at inside. This quantity is what? Because the tau only goes from minus 2t to 2t. So in this interval, it's less than or equal to 1, right? A positive quantity multiplied by less than or equal to 1, isn't this true? This is true, isn't it? I cannot say that here because this could be positive or negative, okay? But I can say it here because this is positive, and this is less than 1. So this certainly, if you multiply by less than 1, this whole quantity after integration will be less than this. Now look at this. If I replace this integral with minus infinity to plus infinity, which one is larger? Anybody? Here I am integrating from minus 2t to 2t. The right side is larger, right? But look at here. The right side is given to be, the right side satisfies this condition because it is absolutely integrable. So the right side is, of course, now, this whole thing is some finite number. It's less than infinity, but that's the same as saying this is some number m2 over 2t. And as t goes to infinity, of course, now this whole thing goes to 0 because m is finite. So we showed that the variance actually goes to 0 as t goes to infinity. Consequently, the process is mean ergodic process. There are few results in Papolis. I'm not going to go over all this because I want to show you a few more types of ergodicity. So you may say, look, I'm not going to worry about it. This is, you need to worry about it because in reality, you would use this always. So you need to know when you can use these expressions. Remember, you collect data, you take the average. You call this the mean. How good is this compared to the actual mean? That's the question. We just went through all this. Most of the cases, this is not represent this, especially in non-stationary cases. So if the process has stationary mean, and then if the variance of this goes to 0, or the correlation matrix, correlation function happens to have these special properties of absolute integrability and so on, then the process will be mean ergodic. So now, what I'm trying to get to it, I want to look at correlation ergodic processes. When can I when can I estimate correlation functions using one sample data? That's the bottom line. Remember, I don't have a stochastic process. I only have one realization. You need to estimate the covariance function because then only you can compute the spectrum, this and that. Correlation or covariance ergodic. Autocorrelation ergodic. That's fine. So what is the problem? Look at here, RXX. So let me replace this by, because we may need that later. So RXX lambda or tau is that expression generally, right? If it is complex, then it is this. The trouble is this is the same as x1, x2, as I explained to you, fx1, fx2, x1, x2, t comma t plus lambda, dx1, dx2, right? So in general, the left side actually may not be even this way. It may be r of t comma t plus lambda. So as I said, and generally you don't have this function. That's the problem. You don't have and you don't have all these realizations. You have one realization. So now the question is, one realization, I can do something like this, you see. Looking here, I can do this. I take that realization, and I can do this. And of course, I will get some function of lambda, right? And I can do an averaging, let's say. But you know, sir, that this cannot be compared with this, because this is a function of time. So if you want to compare, the first condition is what? What do you see here? Cannot be a function of time. What do you call such autocorrelation function? At least second order Whiteson stationary. I mean, if this function is this form, then there may be a chance, right? So we need a second order Whiteson stationarity, not Strickson stationarity, Whiteson stationarity for, you can complete it, for this to represent this. But this is again, this is a random variable, this is a constant function. So if you want a random variable to behave like a constant function, again, we know it's, there should be conditions on its variance. So of course we can go that way, or let me connect this result to, by defining this. Suppose I define a process, look at this. I define this process, I define an artificial process. If this is a stochastic process, this is a stochastic process. So what we are asking is, we want expected value of x of t x star of t plus lambda, which is the same as expected value of y lambda of t. You want it to be what? You want this to look like Rxx lambda, right? See, that's as far as time is concerned, that's like a constant. So what we want is, saying that this function should look like this is the same as saying that on y, what kind of ergodicity you need? On y. Huh? On y of t, for this process, it's a mean to look like this, or mean ergodicity. So for autocorrelation ergodicity in x of t is the same as mean ergodicity in y of t, right? For every lambda. Or the same, if you don't want to go through, you can say that this random variable should look like this. So its variance of this random variable should go to 0, which is the same as saying that, so we want the variance of this quantity, which is, so we will be, how do you compute the, so we will be using this expression, right? Y lambda of t dt minus t to t 1 over 2t, which is the same as 1 over 2t minus t to t, x of t plus lambda dt. So this expression, which is y hat of t, y, right, mu y of mu hat should go to 0, right? So variance of mu y hat should go to 0, right? So that will be, variance is what? So variance is expected value of mu y hat. What is its mean? Look at here. Here, its mean is, you can quickly see, it's going to be this quantity, right? So its variance of mu hat is, because it is here. You take the expected value of this, that's going to be expected value of this. This is this one, that's independent of t, so you'll get it to be mu y itself. So if you want autocorrelation ergodicity, so that's the same as saying the autocorrelation function, we will compute it in this manner, or if it is a discrete data, you take x of n, then you xn plus lambda, and then you sum it up over n. So this is the way you would compute if you have discrete data. You take the data, you shift it by some amount, and complex conjugate it, and multiply. You want this quantity to look like Rxx lambda, except this is unknown. We know that quantity will look like this if the variance of this goes to 0, because the mean is the same as this. So if you do all this, you will again get the same answer, right? So we know the answer. Mean ergodicity is, you need an expression like this. Do I have it here? Look here. Same expression, right? Except I replace Cxx with what? Hello? We want autocorrelation ergodicity for x. That's the same as? No. I mean, autocorrelation ergodicity for x of t is the same as mean ergodicity for y of t. Why is this artificially created function? So the answer is, this will be the same as 1 over 2t minus 2t to 2t. Here you have cyy tau multiplied by 1 minus tau over 2t. This expression should go to 0. Now what is cyy tau? Expected value of, so So Cyy tau is what? Ryy tau minus? Huh? Right, mu y squared. But mu y is what? So that's Ryy tau minus Rxx lambda squared, right? Now let's compute Rxx Ryy for you. Ryy tau will be R expected value of y of t plus tau star. So y of t is expected value of xt plus lambda. This is y of t. Let's say do it in real. Then this is x of t plus tau, x of t plus tau plus lambda. Anybody knows how to do this? So that's the fourth order moment suddenly. So it's getting messier and messier. Anyone? How will you find the fourth order moment of a process? You must have seen it somewhere, no? For any type of random variables? Now remember, actually, this was, if you want to do it properly, that's y star, exit. So here is a star here, there will be a star here, right? Because of the y star. Star here, but y itself is x multiplied by x star.
Shouldn't it be the third and the 12th parts on the star?
Star here, the double star will go away, right? But now this is, generally you will have to leave it like this, fourth order, except when, if x of t is of course a Gaussian process. Now the results are different if it is complex and real, so I'll do it for real. And remember, a few weeks back, didn't I give you, hello, for zero mean Gaussian processes, how to find the fourth order moment? It doesn't have to be zero mean. If it is not zero mean, of course, it's, yeah, you can use those, remember, hello, I gave you the expansion of the characteristic function, right? So you can go home and try to do this. But generally, I think if I call this random variable x1, this is x2, this is x3, this is x4, the result is, for Gaussian, it simplifies like this. You have seen this or no? All right, now you are seeing it then. This is not for complex, it's a different expression, and I don't want to go through all this now. All right, so if you look x1, x2, so that's going to be Rxx lambda, right? And this is going to be Rxx lambda also. So the first term gives you this, right? T2 minus T1, okay. Now x1, x3, that gives you Rxx tau, right? x1, x3, and x2, x4 also gives you Rxx tau. x1, x4, this. So T2 minus T1, that's R plus Rxx, tau plus lambda. And this minus this gives you Rxx tau minus lambda. So that's, then you bring it here and move R squared, so R squared lambda. So this comes Rxx squared tau plus Rxx tau plus lambda multiplied by R. Remember, it's only good for Gaussian. Then you can take this expression and plug it into here if you want. Take this and plug it in here. And then you can again, so most likely if the process is, I think the autocorrelation function is absolutely integrable. I believe this also is correlation ergodic. Why is correlation ergodic necessary? If you want to compute the spectrum, you need autocorrelation function. If you only have data, you can compute the autocorrelation function in this manner, somewhere here, right? In this manner. But this autocorrelation function will represent the true one only under this condition, correlation ergodic. So a necessary condition for correlation ergodic is that the mean of yt should be constant, or x of t should be second order stationary, Whiteson stationary. I was going to do let me show you an application. Okay. I was going to, there are other types of ergodicity. For example, so the whole picture is like this. You measure some data, right, from one realization of a stochastic process. Remember, what you are measuring is only one snapshot, right? One snapshot of one realization, a finite segment. From here, even if you assume the process is Whiteson stationary, then you know this function, if you knew it, you could compute its power spectrum. Now, the question is, how do you estimate it? So that's what we gave. You can estimate a piece of it this way now, right? We know that this quantity goes to Rxx tau, provided this original process is correlation ergodic, and the condition is this complicated condition somewhere here, right? Here. And if the process is Gaussian, that again you can write the Cyy in terms of Rxx. It's messy because you have two expressions now. Look, autocorrelation is squared, it makes sense because y is already the square of a process, right? Or if it generally you measure discrete data, then what you have here is summation xn and this is what you call autocorrelation lag k, and hope is, I mean, this will go to the actual autocorrelation under these conditions. Still, the power spectrum, remember, in the discrete case, the power spectrum is, of course, Rk e raised to minus j omega k, k from minus infinity to plus infinity. So, even if you say that I will so again from here onwards I'm going to sort of touch upon, and you have to do every topic. This topic itself is a long topic. So look at this problem. So we know the spectrum is, of course, sigma Rk So generally you can estimate some of the Rk's, but you're only going to estimate a finite number of them, right? How will you estimate them? Using this expression, Rk hat is 1 over some number of samples So the question is how many samples you need, and underlying assumption is what? This will go to this, that's what we just learned, under this correlation ergodic assumption. So even if this is true, then you are going to estimate a finite number. But you cannot use here you need an infinite number of them. So even if you have this, so if you say I'm going to eyeball it by replace, see this is not a good approximation. I cannot just say if I have only minus n to n, this is, what is the problem with this one? This may not even, this may not be even positive. This is of course positive. What I'm trying to say is that if you use n samples, this may be or may be not positive. Because this is, you can show that this is the convolution of this is a you're only using a window here, right? So this is as good as multiplying by a sink window, and that sink window could go positive and negative. So this is a bad idea. So even if this is the challenge, even if you are able to estimate a finite number of them, how do you find the spectrum? That's a one whole course. So, but I'll give you some ideas next week. Again, I mentioned this because if you want to explore any of this, there is material. All right, we have 5 more minutes, so let me do it. If anybody has access to data, now you have enough tools to do something. I don't know what data it is. Or the other way. Remember, this is what happens in census analysis, right? Height, weight, color of your hair, how many siblings you have, you're a farmer or you ask thousands of questions, you fill up. 4 people, so you have millions of people, lot of credit card companies, lot of people you have here, they may be your spending habits or whatever. So I'm saying you can form a covariance matrix with all this data. I'll talk about this next week. And so you have, let's say, 1 million people. Okay. So now you want to study, see, this is beginning to look like what an estimated covariance matrix. So the question is, we want to study the feature of this. One thing is, how many clusters are there? How many kinds of people are here? Anybody has heard about singular value decomposition or SVD? All right, so you are tired, I am more tired than you, but he is the most tired, right? So we'll do it next week. So remember, next week, then we have half a lecture on 8th, and then 15th, not 8th, 8th of course we have full lecture next week. And then, so you can pick up your homework. If you haven't finished your homework, next week is fine. Because I'll give it to you. Actually, if you have it, give it to me because I'm going to fax you the. or the other way. Remember, this is what happens in census analysis, right? Height, weight, color of your hair, how many siblings you have, you're a farmer or you ask thousands of questions, you fill up. 4 people, so you have millions of people, lot of credit card companies, lot of people you have here, they may be your spending habits or whatever. So I'm saying you can form a covariance matrix with all this data. I'll talk about this next week. And so you have, let's say, 1 million people. Okay. So now you want to study, see, this is beginning to look like what an estimated covariance matrix. So the question is, we want to study the feature of this. One thing is, how many clusters are there? How many kinds of people are here? Anybody has heard about singular value decomposition or SVD? All right, so you're tired, I'm more tired than you, but he is the most tired, right? So we'll do it next week.